Okay, so today I want to talk about two things. I want to talk about how to perform a Wilcoxon Rank-Sum Test in SPSS, and I want to show you how to perform a Kruskal-Wallis test in SPSS. Now, as a reminder, the Wilcoxon Rank-Sum Test is an alternative to the independent two-sample t-test. So we use the Kruskal-Wallis test when we want to determine if there's evidence of a difference among a pair of treatment medians or distributions. The Kruskal-Wallis test is our alternative to the one-way ANOVA. So we use this when we want to determine if there's evidence of a difference between a set of means. So two or more, sorry, when we want to, if there's evidence of a difference between a set of medians, so two or more treatment groups, three or more treatment groups, sorry. Okay, sorry, one more second here. I just need to make sure I have my assumptions for these procedures. All right, so we're going to start with the Wilcoxon Rank-Sum Test. All right, so in this illustration, we are using the data called drug.sav. So drug.sav is available on the course website. And we are interested in determining if at the 5% significance level, there is evidence that patients taking drug A take less time to recover compared to patients taking drug B. Okay, so in SPSS, if we load the drug data, we have something that looks like this. So we have time to recovery in the second column, and then we have two indicators, N_drug and drug. These indicators are the same thing. So drug is just a label for the group values. N_drug is simply the labels transformed. So this is what we would get from recoding the variable A into a quantitative variable. So we have two groups of data here. We have group 1, which is drug A, and we have group 2, which is drug B. And we want to know if there's evidence that the values or the distribution of drug A is smaller than the distribution of drug B. Okay, now let's talk a little bit about the motivation for this approach. Okay, so we'll talk here determining which approach to use. So we have two options. We have the independent two-sample t-test, or we have the Wilcoxon Rank-Sum Test. All right. So if we start off with a simple visualization of the group, so let's say we go graph, legacy dialogues, box plot, then we click simple. Okay, so we put time on the variable axis and we put drug on the category axis, and we click OK. All right, we get the following output. Okay, so what we can see here is that both of the distributions appear to be left skewed, right? So we have the median for A at around 12, and we have the median for B at 15, and we have outliers on the lower end, which would imply left skewness. Okay, so a visual inspection of the data using box plots shows left skewness. All right. Now we can do a similar assessment using histograms. So let's say we go graphs, legacy dialogue, histogram. We put time on the variable axis and we put drug in the row and we click OK. All right, so now we have our histograms and we can see again that we have that evidence of left skewness. Okay, so the histograms also show left skewness. From both visualizations, we have some evidence to suggest that the data is not normally distributed. Okay, now the other thing that we can do here is we can construct QQ plots. Now, QQ plots are a little bit more annoying because you can't split them. Okay, so to construct a QQ plot, what we have to do is take our data for each variable and paste it momentarily into its own column. Right? So I'm just gonna hack these off here for now. So we'll go analyze descriptive QQ plots. So we'll have time and we'll have var1. We'll click OK. Okay, so here's our QQ plot for time. You can see we have this kind of S-like shape here. We have tail activity in the lower area. That would imply left skewness. And then here we have the same type of shape, which again would imply that left skewness. For assignment 4 Q3, are the samples independent, like this example you are doing now? You tell me. What do you think? Okay, well, let's take a look at the data. So this is the reaction.sav data. Okay, so open reaction. Yeah, definitely. So, I mean, one of the key giveaways here is it doesn't admit a paired structure, right? So we have 6 observations in group 1, and we have, what would that be, about 12 observations in group 2. So it certainly isn't going to admit a paired structure because paired structure requires the same number of observations in each group. Furthermore, it requires 2 measurements on each observation. So these would be 2 independent samples. Yeah, so this would be similar to what we're doing now. Does that make sense? Okay. Okay, so what I'm going to do is I'm going to take some of this output and I'm just going to copy it into our Word document so that we can discuss these ideas and then we'll work through the steps of the test. The test itself is very, very easy to perform. This is the most, let's say, taxing part. Finally, a study of the normal probability plots for each group shows gives evidence to suggest that the variable of interest is not normally distributed. Okay. Plots are a bit uneven, but that's the idea. Okay, so here's our 2 QQ plots. From the box plots and from the histograms, we saw evidence of left skewness. When we study the QQ plots for each of the samples separately, we can also see again that evidence of left skewness through the tail behavior and through the fact that this appears to be somewhat S-shaped or curved around the line. Okay, so given these plots, we cannot assume that the variable of interest is normally distributed. Therefore, we should use a Wilcoxon Rank-Sum Test. Okay, so the assumptions of the Rank-Sum Test are a SRS was collected from each population, that the samples are independent, and 3, the populations have the same shape. Okay, so based off of the description in the lab manual, okay, it says that they collected a sample of patients who were independently and randomly assigned to one of the true groups. So this met, so we can say yes, given description in lab manual. And then this would be the same conclusion here. Okay, now for the shape, what we can do is we can take those box plots and histograms that we constructed earlier, and we can use those to judge the shape of the distributions. So here are the box plots. Okay. And here is the shape. Right. Okay, and then what we can say here is, well, I'll just move them up a little bit. So you can write, as mentioned above, the box plots and histograms show that the shape of each population is left skewed. That is the same. Okay, so now we have the hypothesis test. So step 1, step 2, step 3, step 4, step 5, step 6. Okay, so on step 1, we're going to have H subscript 0. And then we're going to have A to 1 equals A to 2. So insert symbol. A to 1. Equals A to 2 versus HA, A to 1 less than A to 2. Right, so we're testing that the mean time for drug A is less than that, or the mean time spent recovering on drug A is less than that on drug B. So we have a lower tail test. Okay, on step 2, we're going to test at the 5% significance level. So we have alpha is equal to 0.05. All right. Now in step 3, we have compute. I can't type. Compute. What's happening to my fingers? Test statistic. Okay, so to do this in SPSS, we need to put our data back together first and foremost. All right, so we're going to go analyze non-parametric tests, legacy dialogues. Okay, so analyze non-parametric legacy dialogue, 2 independent samples. Okay, analyze non-parametric legacy, 2 independent samples. Okay, so then we have time. I should pop these out. So we put time, which is the response in the variable list, and then we put our indicator for the group, which you can see here is the numeric indicator, into the defined variable group. Then we click define groups. Group 1 is just the value 1. Group 2 is the value 2. Click continue. We select the Mann-Whitney test here. Okay, and then we can click OK. Make sure I didn't miss anything. Yep. Okay, so you can see that the test statistics are given in the second table here. All right, so we have our Mann-Whitney U test statistic, we have our Wilcoxon W test statistic, and then we have the Z score based off of the approximation, and then we have a two-tailed p-value. Okay, so here we're gonna have insert pictures from file. Okay, so the test statistic that we are going to use based off of what we did in lecture is W subscript 1, okay, which is equal to 167.5. So this is the sum of the ranks for group 1, right? Our p-value for this test is equal to 0.021 divided by 2 because we're doing a lower tail test, which is 0.105. So on step 5, we can reject H0 since our p-value is less than alpha. And then on step 6, we can conclude by saying at the 5% significance level, the data provide sufficient evidence to suggest that the median time to recover on drug A is less than that of drug B. Okay. Any questions? And that's the Wilcoxon Rank-Sum Test. Where did you go in the menu again? I went to run the test, you mean? So analyze non-parametrics, legacy dialogues, 2 independent samples. Good. It's weird because it's buried in the legacy dialogue thing. You'd think it would just be sitting there, but yeah. Any other questions? Okay, so in example number 2, we're going to use the carbon monoxide data, and we want to determine if there's evidence of a difference among the carbon monoxide levels at the 3 different sites in the data. Okay, so if we load the carbon monoxide data into SPSS, how do I get stuff back that I minimized? Okay. So if we load the carbon monoxide data into SPSS, we have the following data set. All right. So you can see that this data set is actually very similar to what we had for the Wilcoxon Rank-Sum data. So we have one measurement, which is the carbon monoxide value. I don't know if I have units for this. So this is the carbon monoxide level in parts per million. And there's 3 different sites: site A, site B, and site C. Okay, so just like before, we basically have 2 options, okay? Okay, so we have 2 options to answer this question. 1, we have the one-way ANOVA, and 2, we have Kruskal-Wallis test. All right, so let's address the most critical assumption of the test. So we know that the one-way ANOVA test depends on normality. So if we go general linear model univariate, carbon here, fixed factor here, then we click save and we go unstandardized versus standardized residuals. Okay, so I'm building a residual plot right now. Click OK. All right, now what I'm going to do is I am going to build a QQ plot of the residual terms. All right, so here's my QQ plot. So from this QQ plot, what we can see is that we have a deviation from normality, right? So consider the following normal probability plot of the residuals from a one-way ANOVA analysis. Okay, so what this plot is showing us evidence to suggest that the variable of interest is not normally distributed. Therefore, we should utilize a Kruskal-Wallis test to determine if there is a difference in carbon monoxide levels at the 3 sites of interest. Okay, does that make sense? Any questions on that? Basically what I'm doing here is I'm just trying to explain how you would choose between them. So you have 2 options to answer the question, which is the one-way ANOVA or the Kruskal-Wallis. But clearly that normality assumption for the one-way ANOVA is not intact here. So given that that isn't intact, it doesn't make sense for us to proceed with a one-way ANOVA. So in that case, we would turn to the Kruskal-Wallis test. Right. Any questions? Horowitz. Okay, so we're going to utilize the Kruskal-Wallis test. Okay, so the first assumption is that we have SRS and that the sample size is at least 5. Okay, so from SPSS, we can see that we have 8 observations in the first group, 8 observations in the second group, and 8 observations in the third group. From the lab manual, we are told that there are 3 randomly selected industrial sites. So here we can say, yes, lab manual indicates that sites were randomly selected. Further, we have 8 observations in each group. Okay. The second assumption is independent samples. We can say all right, and then the third assumption is treatment populations have the same shape. Okay, so we can verify this the same way that we did for the Wilcoxon Rank-Sum Test. So we can go graphs, legacy dialogues, box plot, click continue. So we're going to put carbon in the variable, site in the category axis, click OK. So here are the side-by-side box plots. All right, and then we can also go graphs, legacy dialog, histogram. We can put carbon in the variable axis. What's going on here? We can put carbon in the variable axis, click OK. And then here are the, come on SPSS, what are you doing? There we go. Okay, and then here are the histograms. Not very informative, but. So from below, we can insert these files. All right, so based off of visual inspection here, we can see that both site A and B show some right skewness. Site C also shows a bit of right skewness, but not to the same degree as sites A and B. Okay, so it would be nice if that median for C was a bit lower, but we do have a really there is a large dispersion between, or a large distance between the maximum in C and Q3, which would imply some skewness. It's just that median is a bit high. It would be nice if that was a little bit lower, because then you would really be able to see that red skewness. But I think that for the purposes of what we're trying to do, we'll assume that they are the same because we don't have a lot of options here. So we will assume that all 3 are a similar shape. Okay, so now we can perform the test. So this is going to be pretty similar to what we saw before. Okay, so we're going to have A/1 equals A/2 equals A/3 versus the alternative that not all population medians are equal. We're going to test at the 5% significance level. Yep. Okay, so now we're going to compute our test statistic for the Kruskal-Wallis. So to do this, oh, sorry, one sec. No. Okay, so sorry, I have to re-say a few things here. Okay, so the Kruskal-Wallis test is performed in SPSS as follows. So we go analyze, non-parametrics, legacy dialogues, K independent samples. Okay, so we have non-parametric tests, legacy dialogues, K independent samples. All right, we move our variable of interest into the test variable list. We move our indicator for the groups into the grouping variable list. We click define range, and we define the range from 1 to the number of groups. So we have 3 groups in this illustration, so we go from 1 to 3. Then we click OK. All right, the output is given in this table below. So if we copy and paste this output into our write-up, we have the following. So this value here is the test statistic. This value here is the p-value. At the 5% significance level, we would then not reject the null hypothesis. All right, now suppose that the significance level was 10%. If the significance level was 10%, then we would have rejected the null. Therefore, we should follow up with a multiple comparison. Multiple comparisons following from a Kruskal-Wallis test are done via a Wilcoxon Rank-Sum Test. For each rank-sum test, we must find the comparison-wise significance level or error rate. Okay, so this is going to be alpha star or actually we'll call it alpha I is equal to alpha E divided by 2m. Okay. M is equal to the number of treatment groups, which is 3 choose 2, which is equal to 3. Therefore, at the 10% significance level, we would have alpha I is equal to 0.1 divided by 2 times 3, which is 0.1 over 6, which is equal to is there ever a calculator around when you need one? There we go. 0.166. All right, now the reason why we need to compute this is because we have to compare the p-value from the rank-sum test to this significance level. Okay, so we have 3 comparisons of interest. We will have median A versus median B. All right. We will have median A versus median C. And we will have median B versus median C. All right, so now all we have to do, because we can use the same assumptions that we used for the Kruskal-Wallis test, we can just take our outline from earlier and we can just modify this a bit. Okay, so this can be multiple comparison 1. So we're going to have eta A versus A to B against the alternative that A to A is not equal to A to B. Okay, the significance level here is going to be what we computed above. Okay, and now what we have to do is we go back to SPSS. So we're running individual rank sum tests in this case. So we're going to go analyze non-parametric legacy 2 independent samples, right? Carbon and site, and then in defined groups, we'll start with variables 1 and variable 2. Okay, so this is the comparison of 1 versus 2. Okay, and then we just have to take our output table here. Okay, and then we can just change this to the new output. Okay, so our test statistic here is 48.5. Our p-value is 0.40 over 2, which is 0.020. So this is larger than the experiment-wise comparison rate, so we do not reject. And then we would say at the 5% significance level, the data do not provide sufficient evidence to suggest that the median carbon monoxide level for group for site A is different from site B. Okay, so this would be the full procedure. Okay, now what we can do instead of doing it this way is we can actually just summarize all of the tests directly. All right. So the way that we could do this is we can just build a table in R. So we can go table, we need, let's say, 3 columns for each of the different comparisons. And then we need the comparison, the test statistic, the p-value, the conclusion. All right. So this can be, for example, well, I guess what we could do is we could just copy and paste the hypotheses here. Let me just do something. I'm gonna table. So insert table. I get rid of all these. Okay, so we can go comparison or hypotheses, test statistic, p-value, decision. Okay, so this will be our first test. This will be our second test. This will be our third test. Okay, so now from above, we actually found the test statistic for the first test. So that's 48.5. The p-value here is 0.040 over 2, which is 0.020. Okay, and then the decision here would be do not reject H0. Okay, and now what we can do is we can go back to SPSS and we can get the information for the second test. So we go analyze non-parametric legacy 2 independent samples. Okay, and then we have to click define groups, and now we're going to do group 1 versus group 3. Right. Click continue, click OK. Okay, so the output here is 58.5. The p-value is 0.317 over 2. All right. That would be equal to 0.16. No. I need to check that one. My brain isn't working anymore. 2 carry the 1, 2. This has to be. Yeah, I gotta check. .1585. There we go. Okay, and then again we would do not reject H 0. Okay, and then the last test. So we would go analyze, non-parametric, legacy, 2 independent samples, define groups, and now we're going to do group 2 versus group 3. So you can see all we're doing is we're just changing the comparison within the Wilcoxon function. Okay, and then this gives us, oh wait, I don't need to divide these by 2. Sorry, these are two-tailed tests. Okay, and then that gives us 51.5. Okay, and then we have 0.082. And then we have do not reject H0. Did I make a mistake? Okay, yeah, so then we can conclude by saying at the 10% significance level, the data, it's actually kind of weird, right? Because we'll say, although the Kruskal-Wallis test provided sufficient evidence to suggest there was a difference among the medians of interest, the multiple comparisons did not suggest any difference exists. Any differences exist. It's kind of interesting, conflicting results in that sense. All right, so those are, well, essentially like 4 examples of the Wilcoxon Rank-Sum Test, which is our independent 2-sample alternative, and the Kruskal-Wallis test, which is our one-way ANOVA alternative. In both cases, the tests are run by going analyze, non-parametric, legacy dialogue. So this is the starting point for both procedures. And then you have 2 independent or K independent. So this would be the Wilcoxon Rank-Sum, and this would be the Kruskal-Wallis test. Once you're inside either of these, you need to specify which groups you're working with depending on the data that you have. But outside of that, it all runs in a pretty straightforward way. When you're setting up the test, so on assignment, lecture assignment, lab assignment number 4, in questions 15, in question 2, question 3, and question 4, those would be the Wilcoxon Rank-Sum Test, the Wilcoxon Sign Rank Test, and the Kruskal-Wallis test, respectively. So you don't need to give the information that I gave today about the rationale for why we would use these tests. You can just work through the assumptions and the hypothesis test like you usually do for these types of questions. but I wanted to give a little bit of insight into how we would choose between them and the rationale for why we would choose between them. And you can see, for example, here in question 2, we have the QQ plotted the residuals for the one-way for the one-way ANOVA experiment, but this is clearly non-normal. So the Kruskal-Wallis would be a natural choice for us to investigate differences among the population medians. Okay, so I will stop there for today. As always, I'll be around until the end of the lab period if anyone has any questions. If not, have a good weekend. Technically, the assignment's due Monday, but I'm going to extend it a couple of days because I just got to this material today. So I wanted to give you a little more time to work through that. And I will, if I don't talk to you or if you don't have any questions, I will talk to you next Friday in our lab session.